For most of modern human history, whether we've inwardly known we're doing it or not, our species has been on a quest for more and more energy. And over the years, centuries, and millennia, we've learned to harness it in many forms, including the first fires in prehistoric times, all-powerful steam across the Industrial Revolution, more fossil fuels in the time since, and renewables heading into the modern age. With all of that in mind, however, we could now be closing in on a new plan for enough energy to sustain humankind indefinitely. And this time, it involves harnessing the power of the sun. This is Unveiled, and today we're exploring the extraordinary breakthroughs science has made toward nuclear fusion technology. Do you need the big questions answered? Are you constantly curious? Then why not subscribe to Unveiled for more clips like this one, and ring the bell for more thought-provoking content. In general, thanks largely to their high energy output and easy availability, it's been fossil fuels such as coal, oil, and natural gas that have been powering our planet's energy expenses since the dawn of the industrial age. But unfortunately, we now know that the use of fossil fuels in the past and today has led and is leading to various and severe detrimental effects on the environment. Alternative renewable energy solutions such as solar and wind do of course offer hope, but scientists are testing other options too, including one possibility which, if it works, could provide us with power on a level with the sun direct. Our sun has been valiantly anchoring the solar system for a long time now. It arrived around 4.6 billion years ago and is comfortably the largest object in the solar system, accounting for 99.8% of its mass. More than 1 million Earths could fit inside it. Energy-wise, NASA says that to match the power from the sun, we'd need to explode 100 billion tons of dynamite every single second. That's a lot of energy, but the sun achieves this through the crucial occurrence of nuclear fusion. Nuclear fusion is a reaction process where typically light atomic nuclei are brought or fused together to make a heavier nucleus, which in turn generates energy. It's what powers the sun, as well as many other stars in the galaxy. Here, in the burning depths of the sun, hydrogen atoms come together to endlessly form helium nuclei. It's happening all over our star all the time, creating effectively endless energy. The sun is essentially a giant thermonuclear reactor in space. The challenge for today's scientists, then, is to take all we know about it and to recreate the star-like conditions to initiate the same reactions here on Earth instead. Fusion science was first demonstrated to a point in November 1952 in the United States, but with the hydrogen bomb. Unlike the atomic bombs before it, which are powered by the atom-splitting process of nuclear fission only, the hydrogen bomb involved a mixture of fission and fusion. Ultimately, it brings hydrogen atoms together to trigger a high-pressure chain reaction and release a tremendous and devastating explosion. The H-bomb is truly terrifying to think about. But channel all of that power into something that isn't a bomb, and there is still potential to solve all of our energy needs. We've known for a long time, however, that it's no easy task, with researchers generally identifying three major problem areas with nuclear fusion: the incredible temperatures involved, the immense pressure required, and then the building of a structure that can contain it all safely. Inside the sun, the core temperature is around 27 million degrees Fahrenheit, and the gravitational force is far greater than anything else for light years around. But recreating that on the ground is naturally tricky. At one time, it had seemed impossible. The earliest attempts toward man-made fusion reactors came in around the 1950s. They were known then and still today as tokamaks, inside of which hydrogen atoms, or more specifically hydrogen isotopes, are heated to extremely high temperatures. Over the years, we've seen how these isotopes can actually be brought to temperatures much higher than even those at the center of the sun, with some reactors reaching tenfold the target, a staggering 270 million degrees and more. In theory, this should compensate for the much lower gravitational pressure here on Earth compared to the fusion conditions inside a star. Hydrogen placed under such extreme conditions converts into a plasma, a soup of ions and electrons, and fusion should follow. But until now, getting to this stage has always, and counterproductively, required far too much energy input. In fact, man-made fusion reactors have always needed more energy to run than they end up producing, which kind of defeats the point of them, no matter how impressive the tech they carry is. But in the year 2021, it appears that we could be about to finally turn the tide. In August, a team at Lawrence Livermore National Laboratory in the United States made headlines after taking a giant step closer to the world's first fusion reaction experiment to successfully reach ignition. That is, to achieve a reaction that does make more energy than it needs to run. Working out of the university's National Ignition Facility, or NIF, the experiment took place inside what's called an inertial confinement fusion reactor. This is different from most traditional tokamak designs because instead of the powerful magnetic fields that are required to power those, inertial confinement fusion uses high-powered lasers to heat up its hydrogen isotopes instead. These lasers get beamed around a series of mirrors inside the reactor and are then focused onto a gold cylinder housing thermonuclear fuel, pellets of deuterium and tritium, both of which are hydrogen isotopes. Once those heat up, they fuse and generate helium nuclei, neutrons, and light. Before those nuclei interact and trigger a self-sustaining chain reaction, thereby generating more helium and more energy. And this is ignition. In a landmark result, the team at NIF confirmed that their experiment, held on August 8, 2021, had generated around 70% of the power required to start the reaction in the first place. It was brought to the brink of ignition before it was ended, and closer than ever before to what's often called the break-even mark, where energy out beats energy in. In other terms, early studies of the results suggest that the experiment also produced a total energy output at least 6 times greater than the previous record. There's no doubt that the NIF team and all others working in the field will hope for even greater efficiency in the future. But in the meantime, the importance of this accomplishment hasn't been lost, and those behind it have found themselves the toast of the scientific community. Now, following the NIF success, we're headed into what looks set to be a critical moment in the technology's history. As well as breaching that all-important break-even point and finally producing a fusion reactor that genuinely makes more energy than it consumes, scientists hope to one day be able to sustain that reaction for several months rather than just for a few moments, as seen during this most recent experiment at the NIF. If and when we get to that stage, then commercializing nuclear energy for power all around the world becomes a real possibility. The future looks genuinely promising too, now that the field is working in earnest with laser fusion, because most researchers and engineers agree that even the tiniest changes to this setup can potentially bring about hugely different results. This means a tweak here, a recalculation there, and perhaps we can up that conversion percentage from 70 to 80 to 100, 110, and more. And suddenly, nuclear fusion on Earth will have moved from the realms of seemingly impossibility to become a much more manageable prospect, and maybe even inevitable. In a mere decade's time, we could well be seeing fusion reactors and plants all over the world map, if progress continues. According to one Dr. Brian Appleby of the Center for Inertial Fusion Studies at Imperial College London and reacting to the NIF results, quote, "We have entered a regime we've previously never been in. This is uncharted territory in our understanding of plasma," end quote. And uncharted territory is perhaps the best phrase for it in general. We are now recreating, with ever-improving accuracy, the environment as seen in the core of the sun. But we're doing it down here, on our own planet, Earth. We're beginning to understand even the innermost secrets of the stars then. And we're working out how to control them for our own needs. And that's why we're on the verge of a truly spectacular breakthrough, with the potential to solve all of our energy concerns forever. What do you think? Is there anything we missed? Let us know in the comments. Check out these other clips from Unveiled, and make sure you subscribe and ring the bell for our latest content.